Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise VTU CBCS scheme network analysis paper solution series. In this tutorial, we shall solve module 3 on initial conditions and Laplace transforms of network analysis paper of June-July 2018. Friends, I prefer to emphasize on basic circuit concepts, strategy and thinking process rather than detailed mathematical steps. I am sure you are already well equipped with required mathematical skills. Hope this tutorial will ignite some of your thoughts. Let's go ahead. Friends, first let us solve question 1. In this question, we are required to determine I0 plus, di by dt 0 plus and d squared I by dt square 0 plus in the network shown in figure. It is also given that the switch K is moved from position 1 to position 2 at t is equal to 0. Further, it is given that the steady state is reached before switching. What does this mean, friends? It means at t is equal to 0 minus, the switch is in position 1 and it could have been in position 1 for a long time or for an infinite time as the circuit has reached its steady state. So, the circuit elements will behave as though t is infinity or t is equal to 0 minus. Hence, at t is equal to 0 minus, the switch is at position 1, L is short and C is open. Incorporating these aspects, the equivalent circuit at t is equal to 0 minus drawn is shown in figure. Friends, observe the network. We find that I0 minus is equal to 0 as C is open, and also observe that IL0 minus is equal to 0 as the branch is open. So, IL0 plus also is equal to 0. But what about VC0 minus? We find that VC0 minus is equal to 20 volts with the polarity shown. Also note that voltage drop across 20 ohm resistance is 0 as I0 minus is equal to 0. Then, how will you substantiate that VC0 minus is equal to 20 volts? Observe that the positive terminal of 20 volt source reaches one end of the capacitance. Similarly, negative terminal of the source also reaches the other end of the capacitance. So, VC0 minus is equal to 20 volts and VC0 plus also is equal to 20 volts. So, it will behave as a voltage source. But we want to find I0 plus. So, friends, we know at t is equal to 0 plus, the switch is in position 2, L is open and C is short. But VC0 plus is equal to 20 volts. Incorporating these status at t is equal to 0 plus, the circuit drawn is shown in figure. Observe the network. We find that I0 plus is equal to 0 as L is open. Here we obtained one answer, friends. Next, to find di by dt 0 plus and d squared I by dt square 0 plus, we need to draw the circuit for t greater than or equal to 0. Observe the network shown in figure. By writing the loop equation, tracing the loop in the clockwise direction, we get R into I minus 1 upon C into integration I dt plus L into di by dt is equal to 0. Note that 1 upon C into integration I dt is Vc0 plus and we are tracing this voltage drop from positive to negative. Hence, it is minus 1 upon C into integration I dt. Hope you understood it. Friends, equation 1 written is a general equation which holds good for all time t. Hence, it also holds good for t is equal to 0 plus. By substituting t is equal to 0 plus for t in equation 1, we get equation 2. But we know 1 upon c into integration I0 plus dt is equal to Vc0 plus is equal to 20 volts and I0 plus is equal to 0. So, substituting these values in equation 2 and solving, we get di by dt 0 plus is equal to 20 amperes per second. Friends, now to obtain d squared I by dt square 0 plus, by differentiating equation 2, we get r into di by dt 0 plus minus I0 plus by c plus L into d squared I by dt square 0 plus is equal to 0. By substituting R is equal to 20 ohm, di by dt 0 plus is equal to 20 and L is equal to 1 Henry, and solving, we get d squared I by dt square 0 plus is equal to minus 400 amperes per second square. Hope you understood it. Friends, next we shall solve question 2. In this question, we are required to determine the voltage drop across the capacitor Vc of t using Laplace transforms. It is given that the switch is closed at t is equal to 0. Friends, first let me explain the strategy to solve this problem. Since we are required to use Laplace transforms to find Vc of t, there is no need of finding the initial conditions. Understand this. But the entire circuit is to be transformed into S domain, friends. We know that when DC voltage is switched, it will behave as a step function. Hence, 10 volts DC source, when transformed, it becomes 10 divided by S. This you know. Resistance will remain as it is. Impedance form of transformed capacitance will be 1 upon Cs. So, 2 farad capacitance, when transformed, it becomes 1 upon 2S. Incorporating these aspects, the transformed circuit drawn is shown in figure. Friends, hope you know that when all the elements are transformed into S domain, they become the scalar quantities. Hence, we can use suitable network solving technique to solve for Vc of S and take the inverse Laplace transform to obtain Vc of t. So, observe the network. The network has two junction nodes. One is Vc and the other is a reference node. By writing the Kirchhoff's nodal equation for node Vc, we get Vc minus 10 by S divided by 10 plus Vc by 10 plus Vc upon 1 upon 2S is equal to 0. By using simple algebra and solving for Vc of S, we get Vc of S is equal to 0.5 divided by S into bracket S plus 0.1. Friends, using partial fraction expansion, we can write Vc of S is equal to A divided by S plus B divided by S plus 0.1. By solving for A and B, we get A is equal to 5 and B is equal to minus 5. By substituting the values for A and B in the equation for Vc of S and solving and rearranging, we get VC of S is equal to 5 into bracket 1 upon S minus 1 upon S plus 0.1. By taking the inverse Laplace transforms, we get Vc of t is equal to 5 into bracket 1 minus e to the power of minus 0.1 t. Very simple, isn't it? Friends, next we shall solve question 3. In this question, we are required to find V0 plus dv by dt 0 plus and d squared v by dt square 0 plus in the network shown in figure. It is given that the switch is opened at t is equal to 0, meaning it is in closed position at t is equal to 0 minus. In other words, it has remained closed for a long time or for infinite time and the circuit has obtained its steady state. So, inductance at t is equal to 0 minus behaves as short. Also, at t is equal to 0 minus, the switch is at closed position. Incorporating these aspects, the equivalent circuit at t is equal to 0 minus drawn is shown in figure. Observe the network. Since L is short, R also is short circuited. So, the entire current of 2 amperes will flow through the switch. Hence, IL0 minus is equal to 0 and IL0 plus also is equal to 0. But friends, we want to find V0 plus. So, we need to draw the equivalent circuit at t is equal to 0 plus. We know that at t is equal to 0 plus, the switch is open, L also is open. Incorporating these aspects, the equivalent circuit at t is equal to 0 plus drawn is shown in figure. Observe the network. Now, since L is open, 2 ampere current will flow through 200 ohm resistance. So, V0 plus is equal to 2 into 200 equal to 400 volts. That's very simple. To find dV by dt 0 plus and d squared v by dt square 0 plus, we have to write the circuit for t greater than or equal to 0. So, friends, the circuit drawn for t greater than or equal to 0 is shown in figure. Observe the network. There are two junction nodes. One is V of t and the other is a reference node. By writing the Kirchhoff's nodal equation for node V of t, we get minus 2 plus V divided by 200 plus 1 upon L into integration V dt is equal to 0. Note, 1 upon L into integration V dt is the current through the inductance. Friends, equation 1 is a general equation which holds good for all time t. So, it also holds good for t is equal to 0 plus. We want dV by dt 0 plus. So, differentiating the nodal equation obtained at t is equal to 0 plus, we get 0 plus 1 upon 200 into dV by dt 0 plus V0 plus divided by L is equal to 0. We know V0 plus is equal to 400 volts. Hence, by substituting for V0 plus and solving, we get dV by dt 0 plus is equal to minus 80,000 volts per second. Friends, to obtain d squared V by dt square 0 plus, by differentiating equation 2, we get 1 upon 200 into d square V by dt square 0 plus 1 divided by 1 into dV by dt 0 plus is equal to 0. Note, L is equal to 1 Henry. By solving for d square V by dt square 0 plus, we get d squared v by dt square 0 plus is equal to 16 into 10 to the power of 6 volts per second square. Hope you understood it. Friends, finally, we shall solve question 4. In this question, we are required to obtain the Laplace transform of the periodic waveform shown in figure using gate function. We know that the Laplace transform of a periodic waveform f of s is equal to f1 of s divided by 1 minus e to the power of minus st, where f1 of s is the Laplace transform of the first period of the waveform and t is the period. So, to get f1 of t, we can use gate function. Friends, gate function is obtained using step functions. During time other than 0 to t, the function is 0. So, unit gate function is shown in figure. Using this unit gate function, we can obtain the waveform of the first period of the given periodic function as shown in figure. Let us call this function as f1 of t. Now, we have to obtain the equation for f1 of t by representing the waveform by piecewise defined functions. Observe the waveform. Hope you can identify a positive step of a units at t is equal to 0 as shown. Let it be f11 of t. We know f11 of t is equal to a into u of t, but the given waveform traces down at t is equal to 0. So, we have to add a negative ramp of slope minus 2a divided by t at t is equal to 0. Let this function be f12 of t and f12 of t is equal to minus 2a divided by t into r of t. But friends, observe that f12 of t traces down beyond minus a as shown. So, to bring the trace back to trace horizontally, we have to add a positive ramp of slope 2a by t at time t. Let this function be f13 of t, and f13 of t is equal to 2a divided by t into r of t minus t. Now, we obtain the trace which traces horizontally along minus a units. Hence, to bring the trace to proceed along the x-axis as required, we need to add fourth function which should be a step function of a units at t is equal to t seconds. Let this function be f14 of t and f14 of t is equal to a into u of t minus t. Using these piecewise defined functions, we get f1 of t is equal to f11 of t minus f12 of t plus f13 of t plus f14 of t. By substituting for all the four functions, we get f1 of t is equal to a into u of t minus 2a by t into r of t plus 2a by t into r of t minus t plus a into u of t minus t. By taking Laplace transforms, we get f1 of s is equal to a divided by s minus 2a by t into 1 divided by s square plus 2a by t into 1 divided by s square into e to the power of minus st plus a by s into e to the power of minus st. Friends, next is only simple algebra. By rearranging and solving, we get f1 of s is equal to 2a divided by st into bracket t by 2 into bracket 1 plus e to the power of minus st minus 1 divided by s into bracket 1 minus e to the power of minus st. But we know f of s is equal to f1 of s divided by 1 minus e to the power of minus st. Therefore, by substituting for f1 of s and solving, we get f of s is equal to 2a divided by st into bracket t by 2 into bracket 1 plus e to the power of minus st divided by 1 minus e to the power of minus st minus 1 upon s. Hope it is clear to you. Friends, to strengthen your basic circuit concepts and develop your thinking process, I suggest you go through my textbooks, Network Analysis Made Easy, Basic Electrical Engineering, Basic Electronics, and Linear Integrated Circuits and Applications. You also can refer my CET handbook on electrical and electronics engineering for preparing for your competitive examinations. Friends, all books are available online. Thank you for watching this video.